Okay, so here's a solution video for topic 9.3 interference, the Mr. G formative assessment situation. So there's 2 pages here. Let's begin at the beginning, and we're talking first about Gillen's double slit interference. I'm trying to rotate this so that it's actually straight. I think that's good enough. I don't know why they gave us so little room, but we can zoom the worksheet, so it gives me more room to work with. So this is actually topic 4.4, going back to SL physics. And of course, our formula is going to be S equals lambda D over D, where S, lowercase s, is the distance between the 2 fringes. D is the distance between the 2 slits of the 2 double slits. Big capital D is the distance to the screen, from the slits to the screen, and lambda is the wavelength. And so that's kind of basic. We get that the distance from the central maximum to the first maximum or second maximum, I don't know, if you're maybe the central maximum is the zero maximum. Anyway, that S is 1.07 times 10 to the negative 2 meters, or 1.07 centimeters. Next question. Coherent light, unknown frequency, projected on a double slit, slit separation, 0.450 millimeters, screen 5.5 meters away. Separation between the maxima is 1.5 centimeters. What's the frequency of the light? So we're using the same equation here, but we're solving for lambda, and then we're going to convert it to frequency with V equals F lambda, where V is the speed of light, 3 times 10 to the 8 meters per second. Let's go. Okay, let's go with what we have so far. S equals lambda D over D. Therefore, lambda is SD over D, S lowercase d over a big D. I know V equals F lambda. V is the speed of light. So if I solve for lambda, I get lambda is C over F. I sub in C over F for lambda. So there's my lambda, and there's my C over F right there. And so I just flip both sides to get F in the numerator, and then multiply both sides by C to get F by itself. Okay, so slip in C for the speed of light, D for the distance to the screen, S for the separation between the maxima, the 1.5 centimeters, and then little d for the slit separation, and I get 2.44 times 10 to the 14 hertz for the frequency. Okay, let's look at number 3. We have some interference patterns with a scale in centimeters, and it says monochromatic light passing through varying number of slits, each with a slit width of 15 micrometers and a slit separation of 45 micrometers. Distance from the slit barrier to the screen is 3.5 meters. What is the wavelength of the light? So looking at the pattern we have here with, hold on. Okay, so looking at the pattern we have here, we have 5 different slit patterns. We have single slit, and then 2, 3, 4, and 5 slit. But basically all that does is it changes the intensity of the maxima and kind of spreads them out more. But the actual positioning of the maxima does not change. And so if we go back to the information that we're given, we have slit width. Now slit width, that actually goes into theta equals lambda over b, which is actually the single slit diffraction pattern. That's the overall envelope that's going to control the width of the central pattern. We're not going to need that yet. In fact, I don't think that applies to any of these questions, but the slit separation does matter. That's the separation from slit to slit. The distance from the slit barrier to the screen, that's big D, that does matter. And then the one thing that we are missing is the separation from the central maximum to the first maximum, from the 0 maximum central to the first maximum, but that's why we have this scale down at the bottom of this image. And so I drew 2 lines here, one to match up with the center of the 0 maximum, and another to line up with the first maximum. And I can tell from my scale that this works out to be roughly 0.7 centimeters. That's going to be my S, my separation from the central maximum to the first maximum. So let's bring that back to the problem for S is lambda d over d. Okay, terrific. It's time for some revisions. I'm glad I caught it now. All right, so first of all, let's back up a bit. And let's see. This guy is good. I wrote that correctly. That's why this frequency makes sense. 2.44 times 10 to the 14 hertz. This is totally not working out for me, and that's because I wrote the formula wrong. It's not lowercase d over capital D, it's capital D over lowercase d. Let's fix that. Isn't it so much fun when they use the same letter? Yeah. So let's fix it. There we go. Therefore, lambda is S lowercase d over d, making our formula down here. We'll change some numbers around. Okay, let's give that a go. 9 times 10 to the negative 8 meters, which is a much more reasonable number. The only issue I have with that is that the color of the light over here is red, and it looks like a red visible light laser, and red light is like something around, I want to say 3 to 400 nanometers. Oh wow, I'm thinking frequency. Okay. Yeah, so I'm sorry, red has a longer wavelength. I'm glad I verified that. That bumps up to 750 nanometers. But point is that this answer gets me 9 times 10 to the negative 8 is 90 nanometers. That's nowhere near 750. So I don't really know what light they're using here. But the numbers do make sense. We got the 0.7 times 0.7 centimeters for the separation from this primary maximum to the first maxima over here. That would be S. D, the 45 micrometers, that's the slit separation. We have that. And then we have the distance from the barrier to the screen, 3.5 meters. And I just double check my math, and I do get 9 times 10 to the negative 8 meters, which makes sense in terms of a wavelength. That just seems like a rather short wavelength for visible light. It's not even in the hundreds of nanometers. It's in the tens of nanometers, so I don't really know what's up with that. Anyway, and I still don't think that the slit width plays a role, because slit width plays a role in the creation of the envelope that modifies the pattern. The envelope I'm talking about is this area here and this area here, like that. That envelope is created by the single slit diffraction pattern, but that does not affect the wavelength of the light. So anyway, let's move on to number 4. Let me clean this up. Number 4, label the number of slits each image is produced by. So as you increase the number of slits, then the central, the maxima become tighter and more intense. And so we start off at the top. Let me get my yellow going on here. So this is one slit. That's a single slit pattern that pretty much just has the envelope with no interference effects. We just have that broad central maximum and no other effects there. And then it starts to break up as you introduce two slits. You get the two slit interference pattern that's modulated by the overarching single slit diffraction pattern. So that's 2. And as you increase the number of slits, then you don't increase the number of maxima, they just get tighter and brighter. The brightness is hard to see here, but you can see that they are getting tighter. These guys are more spread out, and these guys are tighter, more intense. So then as we move downwards, we increase the number of slits, and the maxima become more focused and more intense with greater gaps between them. Okay, let's look at number 5. So number 5 says the intensity of the central maximum of the single slit is 1.25 milliwatts per meter squared. What's the intensity of the central maxima of the 4-slit pattern? So my understanding is that the intensity of the maxima increases as the square of the number of slits. So, like for instance, for the 2-slit pattern, there are 2 slits, so 2 squared is 4, and so the intensity of each maxima would be 4 times what it is for the single slit. For 3 slits, that would be 9 times the intensity of what it is for the single slit. 4 slits would be 16 times, and 5 slits would be 25 times. So it's asking for the 4-slit pattern. Let's, where's my black? There we go. 4-slit pattern. And so yeah, we go from 1 slit to 4 slits, and so intensity is proportional to slit count. At least that's my understanding. Therefore, 4 slits. 4 slits means, let's see, 4 squared, that would be 16 times intensity, I'll say I naught, for the single slit. And so our single slit is 1.25 milliwatts per meter squared, so 16 times that yields 20 milliwatts per meters squared. I just realized I is proportional to slit count squared. I forgot to add that squared in there. Or at least that's my understanding. I can't actually find this in the SOCOS text, and the SOCOS text is kind of like the go-to for IB physics, so I'm not entirely sure this is testable, but I mean, like, that's not a hard thing to recall, that intensity is proportional to the square of the slit count, so just be aware of that. Let's proceed. So 5-slit interference pattern, sketch the intensity versus angle from central maximum in the space provided, taking into account the single slit modulation envelope. Why the 5-slit? That's kind of annoying, but so the single slit modulation envelope. So there's the single slit modulation envelope, and then we have, let's see, 5 maxima in the middle and 2 on the outside. They used red, so shall I. Now let's see, we have central maximum, 2 to the sides, 1, 2, and then 3 beyond that. So that gives us 5 central spots. And then over here we have 2 maxima, and over here we also have 2 maxima. But again, basically the way this works is that if the single slit modulation pattern weren't there, then you would just have maxima all of the same intensity, pretty much just like a sine curve running all the way through, but that sine curve is modulated by the envelope encompassing that sine curve, which is provided by the single slit diffraction pattern. Okay, so for number 7, it says we have a diffraction grating with 650 lines per millimeter. Monochromatic light is incident on the grating. 3rd order maximum observed at 15 degrees to the straight through direction to determine the wavelength of the incident light. So to find lambda, we use the diffraction grating equation, and lambda equals d sine theta, where n is which maximum we're talking about. And it says that this is a 3rd order maximum, so in this case n equals 3 for 3rd order maximum. Lambda is what we're solving for. D is the distance between the slits. We're going to need to figure that out. It says that it's 650 lines per millimeter, and we know that the diffraction grating is 650 lines per millimeter, or per 1 times 10 to the negative 3 meters. We can just flip that over to figure out how many meters per line. So I would say 1 millimeter per 650 lines That gets us about 1.5 micrometers, so 1.53864, etc. Times 10 to the negative 6 meters per line. That's going to be the D. D in this equation is how far apart each line is. Theta, of course, is 15 degrees, and I figure we should be in radian mode, so let's work the math. We're solving for lambda here. Scratch that, I rethought it. They're giving me 15 degrees, so if the angle is given as 15 degrees, then I should be using degree mode to process sine of 15 degrees, aside from the fact that when you use radians, you get something like a half a meter or something bananas. So just not right. So let's try that again. And yes, this answer makes a lot more sense. We wind up with a wavelength of 1.33 times 10 to the negative 7 meters, which would be 133 nanometers. That makes a lot more sense. Box that off. La la la. All right, next. Also wanted to note that's degree mode, not radian mode. So number 8's an interesting question. It wants to know how many orders of light can be seen. And so the orders are actually given by n, in n lambda equals d sine theta, where theta is the angular separation from the central maximum, from the zero maximum, to each of the maxima, each of the orders of the maxima. So you got first, second, third, etc., etc. But there's a limit. It says, hint, theta must be less than 90 degrees. Why is that? And that has to do with the way theta is measured. So if you have from the slits to the screen, the maxima, there's the primary maximum, and then all of the secondary maxima, etc., etc. Like there's the first order, and then there's the angle theta to that first maximum, and then you have all of the other maxima that go along with that. And so that would be the second one, and the third one, and the fourth one, etc., etc., as the angle gets bigger and bigger. And so it's kind of like for each, if we look at n lambda equals d sine theta, as n increases, lambda and d are going to be the same, but theta will increase as well. So for each order, we have 0, 1, 2, 3, etc. For each order of maxima that we're dealing with, there's going to be a bigger and bigger theta, except that there comes a point where the angle gets so big that it's just never going to strike the screen, and that would be 90 degrees from that central line. So once you get once theta, this theta going away from the central line, this guy, once that gets to 90 degrees, then that light is just not going to strike the screen. So when it says hint, theta must be less than 90 degrees, why? Because that 90 degree a light ray at 90 degrees to the center line will not hit the screen. So that's why. So then it's like, okay, well then how do you figure out how many orders are going to show up on the screen? And I'm not even concerned about the envelope and how the envelope moderates the intensity. I'm just saying how many orders are actually going to show up on the screen. And so the way you figure that out is you set theta to 90. So it's like if I say n lambda equals d sine theta, and say theta is 90, what's the n value when theta equals 90? And then the last order you can see is the n that's beneath that number. So let's figure that out. All right, so we have 1.53864 times 10 to the negative 6 times the sine of 90 over the wavelength Of course, we know that the sine of 90 is 1 equals 1. So it's really just d over lambda. And we wind up with an n value of 11.5687. So that means that we are not going to see the 12th order maxima, because 12 is not going to show up on the screen. In fact, the last one to show up on the screen is order 11. And so it said, including the 0 order, so including 0, we wind up with 12 orders. 12 orders if including the center guy, the central maximum. We wind up with 12 orders on the screen. So that's 0 plus an additional 11. But in terms of the orders 1, 2, 3, 4, 5, etc., we're not going to see n equals 12 because you hit the 90-degree mark after the 11th order. I'm just curious, if n equals 11, I wonder what the angle actually is. Let's just figure that out. So 72 degrees, all the way out at 72 degrees. That 11th order will hit the screen eventually, but that's the last one that's going to strike the screen. So we have 11 orders plus the center to give a total of 12 orders. All right, that's the first page. Now let's move on to the next page with number 9. So the questions for number 9 really kind of get at what we need to be considering for thin film interference, and that has a lot to do with what happens when light encounters a boundary between two different mediums, or when any wave encounters a boundary between two different mediums. Okay, so question 9. So I think I said before that this has to do with the thin film derivation, but if a wave enters a boundary where the wave speed is lower, and that's in most cases with light, because light in air has a speed that's roughly that of vacuum, so if it enters anything, plastic, glass, anything, water, it's going to have a lower wave speed, and in that case, the reflection off of that boundary will be completely out of phase. It will reflect inverted. But then if you have a reflection off of a boundary where the wave speed is higher in the new medium, then that reflection is actually going to be in phase with the original wave. And then finally for number 3, the transmission is always in phase with the original wave. Okay, let's keep on going. We're looking at number 10. It says thin plastic film suspended in air, illuminated by a monochromatic light with a wavelength of 650 nanometers. The index of the film is 1.35. Calculate the minimum thickness of the film needed for destructive interference to occur in light when viewed from the side of the light. And so we have this is the destructive interference condition, and we're going from air into a material that has an index higher than air, so here we go. And the thin film destructive interference equation is on the data booklet. 2dn equals m lambda. So let's write that down. Well, let's write down our given information first. Then we can write down the equation, and we can go from there. So we know the wavelength, and we know the index. And the problem is asking for the condition of destructive interference. And so we have 2dn equals m lambda. And then m is just an order of magnitude. So it says minimum thickness. So that would mean like kind of 1 lambda. That would be kind of like the first order there. The minimum thickness of the film. So that m, the m count, would be 1. Normally they would use n for a count, but n is already being used by index of refraction. So now we're using m instead. And it wants the thickness of the film, so that would be d, so we're solving for d. I mean, sheesh, 241 nanometers, that's pretty thin. That's why they call them thin films. All right, so let's move on to number 11. Okay, so for 11, we're talking about oil on water, going from air into oil and then into water. The index of oil is 1.4, the index of water is 1.33. And so even though the oil is on water, the oil still has a higher index than the water does. So in terms of the physics, this is kind of like the same as it's going from air into a thin film and then back out into air. So it's like low index to high index, and then on the other side, back low index again. So in terms of whether we'll see whether there'll be constructive or destructive interference, the relationship is given in the data booklet. So let's actually draw a little sketch to illustrate. Let's go. Let's zoom in. I'm actually going to use the line, since I can zoom this thing so much, I'm going to use these lines as the boundaries between my media. Okay, let's mark this up. Okay, so first of all, we have the reflection off of the oil surface coming in from air. Oh, my fade is not looking that great. Let me fix this here. That's better. So when we reflect off of the air-oil boundary, the reflection is going to be phase shifted 180 degrees because the index of oil is greater than that of air. If the index of oil were less than that of air, then there would be no phase shift in the reflection. Forgive my shaky hand, but that's the transmitted ray going from air into oil, and when we have transmission, there is no phase shift. So the transmitted ray has the same phase as the original ray. And keep in mind, it said that this was near normal to the surface, so even though I'm drawing these as angled rays, I'm ignoring the refractive effects because I just drew them as angles for illustrative purposes. But for the purposes of the physics, we're saying that they are normal or near normal, so we're not worried about the refraction. If they did not come in normally, we would have to concern ourselves with the refraction, but that's another layer. This is enough. Anyway, so no phase shift for the transmitted ray, but now we're reflecting from water, reflecting off of the oil-water boundary, and since water has a lower index at 1.33 than the oil does, let me look at the sheet, the oil has an index of 1.4, there will be no phase shift in the reflection. And then again, the transmitted ray has the same phase as the ray in oil as it goes from oil to air. When it transmits from oil to air, there is no phase shift, so it maintains the same phase. So now we can see that the reflected ray from the air-oil boundary and the reflected ray from the oil-water boundary, they are 180 degrees apart. So under these conditions, we would have completely destructive interference. And so you wouldn't see these rays unless unless in terms of the width of this, in terms of the path difference, for how, like, the distance that the ray has to travel through that the thickness of the oil, it totally matters in terms of how many wavelengths that is. And so based on what I just drew, we get destructive interference if 2 times the thickness of the material. So hold on one second, let me erase some of my notes here. Okay, so there's the thickness of the oil, that would be D. N would be the index of the oil, or whatever the film is. In this case, it's the oil. And then M is just an integral number, so multiples of the wavelength. And of course, lambda is the wavelength. Now you can also get a constructive interference condition if instead of whole wavelengths, you get half wavelengths. So that would be M plus a half. So it's like 1.5, 2.5, 3.5. Which kind of makes sense because of the way I explained it earlier. You can say, like, well, if the ray that reflects off the air-oil boundary and the ray that reflects off the oil-water boundary, if they meet up here, up at the air where the person's eye is, person observing, where the person's eye is, then you'd be like, well, they're phase shifted, they're completely out of phase, you get destructive interference. But what if that 2dN, in terms of the index of the oil and the path that it's following within the oil, what if that's a half wave? So basically, if that path difference causes a half of a wave, then half of a wave that's then phase shifted 180 degrees. Now we're back to in phase, and now we have maximum constructive interference. And so that's the condition. That constructive interference is the one that we're getting at for this question, because it's not that we're not seeing orange, we are seeing orange. So we want to use the constructive interference condition, because it says it's not that we're not seeing the color, it says we are seeing the orange color. So we're not destructively interfering, we're constructively interfering, so that we do in fact see the light. So let's work the math. Actually, working the math is 12 and 13. 11 is kind of explaining what I just said, but let's zoom out so that these lines that we're using for boundaries can actually be used for writing an answer to the question. So in the space they provided, that's kind of like the summary that I put down. It's based on the relative indices of air, oil, and water that causes the phase shift relationships that we just described over here. And the that makes that formula valid, that for constructive interference, if 2dn equals m plus 1/2 lambda. And if they want any more in depth, we would have to like include this diagram in terms of the phase shifts, etc., etc. But I think that kind of satisfies the answer. Then number 12, calculate possible thicknesses of the film in the orange region. So we're using 2dn equals m plus 1/2 lambda. So let's go from there. They certainly don't give us a lot of room. Let's zoom in again. So there we go. That's the minimum thickness that the oil can be, is 319 nanometers. But then it could be multiple thicknesses. And actually, I'm surprised they asked for the possible thicknesses before they asked for the minimum thickness, because the minimum thickness is when m equals 1. But then multiples of that, and if I use multiples of m instead of the first order m, then m equals 2, m equals 3, m equals 4, my thickness, my thin film gets less thin, gets chubby. So we have 319 when it's the thinnest, and then 531, 743, 956 nanometers as we go. These look like decimal points. Hold on. There. So there we go. 319 is the minimum, and then going up by seemingly 212, 531, 743, 955, etc. So that is the answer to 12 and 13. Then the last question is 14. I believe it's the last question. Yes. 14, talking about magnesium fluoride. So we're on a thin layer on an optical lens made of glass of index 1.4. What thickness should the magnesium fluoride be so that light with a wavelength of 595 nanometers is not reflected from the lens? In other words, destructively interfered. So 14 is different than 11 through 13 in that you're putting the, you're putting the thin film on something with a higher index. With the oil film, that oil was on top of water, which had a lower index. So if you put the thin film on top of something with a higher index, then the constructive and destructive interference equations switch, they trade. I can show you why that's true. Okay, so here's the deal. You have the incoming ray with a phase of phi, and when it transmits into the magnesium fluoride thin film, any transmission maintains the same phase. When the air reflects off of the magnesium fluoride has a higher index than air, so there's a 180 degree or pi phase shift. Okay, cool. But then once we're going from the magnesium fluoride to the glass has a higher index than magnesium fluoride. It's said in the problem. So yeah, the glass has a higher index than the magnesium fluoride, so then the reflection off of the glass is also going to have a pi phase shift, which is different from before. When we were dealing with the oil on the water, or say like a soap bubble, thin film with air on either side, the reflection at this point will be off of a lower index, so there would be no phase shift. But now I'm reflecting off of a higher index, so there is a phase shift. And then as that transmits from the magnesium fluoride back out into the air, now that transmitted ray has the same phase as the original reflected ray that reflected off of the air magnesium fluoride boundary, which is a different geometry than, well, geometry? Phase relationship? I don't know. Call it what you will. But going back to our drawing from earlier, you can see that at the top in the air, then the reflected rays, ray that reflected off of the air oil boundary and the ray that reflected off of the oil water boundary have a phase relationship of being completely out of phase. They have one ray that's phi plus pi, and then you have the other ray that's just straight up phi. Whereas in this guy down here, they have the same phase relationship. They're both phi plus pi. So then, using the relationships that I said before about destructive interference if it's a whole number of waves, constructive interference if it's a half number of waves. But since the phase relationship is opposite down here, then those two formulas then flip. So the relationship that's in the data booklet, these guys here, that's from the data booklet, destructive interference 2dn equals m lambda, constructive interference 2dm equals m plus 1/2 lambda. That is true if the thin film is on top of a material that has a lower index than the film itself. If the film is on something that has a higher index than the film, like in this case, magnesium fluoride on top of glass, then those two equations switch. Let me write that down. So those are the data booklet equations, but we switch constructive and destructive. So yeah, we switch destructive and constructive is if the n of the second material, third material if you're counting air as your first material. I'm not. But if the second material, whatever the thin film is on, has an index greater than the thin film itself. So keeping that in mind, that's this situation here. I think they actually asked a question in number 14. Let me check. Yeah, so they want, this is an anti-reflective coating, and it says what thickness should the film be so that the light of 595 nanometers is not reflected from the lens. So if I'm trying to kill the reflection, I want to destructively interfere the light. So I want the destructive interference condition, but having switched what the data booklet said, because again, the film is on top of something with a higher index. And so I set M to 1 to be the minimum thickness for this film. So when we work the numbers, we get a thickness of 326 nanometers. And there you have it. And that's how anti-reflective coatings work. All right, 14 was the last question on the worksheet, so that is the end of this solution video.